Let's start out with a simple SAN that has two switches in the middle, a host on the left and a storage array on the right. The first set of ports that we'll show are the N ports, short for node ports. N ports exist in what we sometimes refer to as end devices. That's servers and storage arrays are not switches. Switches are not end devices. And if we update our diagram, we can see that N ports connect to F ports in switches. F ports are fabric ports. And as we mentioned just a minute ago, switch ports start out their life as G ports and dynamically recognize when N ports connect to them and automatically configure themselves to be F ports. So that's N devices connecting to switches covered off. N ports exist in N devices and connect to F ports in switches. Now let's connect our two switches together to form a two-switch fabric. If you look closely, you'll be able to see that the ports on either end of the switch-to-switch links are showing as E ports. E for expansion ports. Again, just like with the F ports, E ports start out as G ports and automatically configure themselves to be E ports when they recognize that another switch is on the other end of the link. Now a quick point on part of the reason why G ports in switches are able to automatically configure themselves as F ports or E ports. Basically, anytime a new link is established to a switch, that is, anytime a device appears on the other end of the link to a switch port, the device connecting to the switch performs a login to that switch. And as part of this login process, the device identifies itself as either an N device or as another switch. If the device logging in identifies itself as another switch, the port will configure itself as an E port, whereas if it identifies itself as an N device, the port will configure itself as an F port. Now then, we call these links between two switches inter-switch links or ISLs, and these ISLs can be trunked, and by trunked we mean that multiple ISLs between the same two switches can be bonded into a single logical link with the combined bandwidth of both ISLs. If you know Ethernet networking, think of this trunk as more of a port channel. You should be aware of this as well. The term trunk in fiber channel is not the same as trunk in the Ethernet world. When we refer to trunking in fiber channel, we're referring to what you consider more of a port channel in the Ethernet world. Let's look at a simple example. We'll assume that each of the two inter-switch links between our two switches operates at 16 gigabits per second. Right now on our diagram we've got two separate 16 gig ISLs. Now let's trunk them. What we now have is a single 32 gigabits per second logical ISL. Cool, but what's the point? What's the difference between having two independent 16 gig ISLs versus a 32 gig trunked ISL? Well, for one, you get automatic load balancing across both links, meaning that each link shoulders its fair share of the burden. If you don't have trunking, you have to manually load balance, and you could end up with one link doing most of the work. Also, if one of the ISLs fail, we get less disruption to the fabric if we have a trunked ISL. So let's quickly summarize this slide. Initiators and hosts are considered as end devices on the SAN. Their HBA ports operate as N ports, short for node ports, and connect to F ports or fabric ports in a fiber channel switch. When a link comes up between two switches, the switch ports at each end of the link configure themselves as E ports, expansion ports, and the link between them is called an inter-switch link, commonly shortened to ISL. Last, but certainly not least, ISLs can be trunked for aggregated throughput, better load balancing, and improved fault tolerance. While talking about ISLs, it's a good time to mention oversubscription, as ISLs are often oversubscribed. Imagine this, an edge switch with 24 ports all running at 8 gigabits per second. Now let's imagine that 22 of the 24 ports are being used to connect to servers, and the remaining 2 used as a trunked ISL. Theoretically, the 22 hosts could push over 150 gigabits per second, but the trunked ISL to the core, where the storage is, only has 16 gig of aggregated bandwidth. Basically, the trunked ISL is massively oversubscribed and will become a major bottleneck if, all hosts decided to utilize their entire bandwidth. But this tends not to be a problem because we know that not all of our hosts will ever push their entire bandwidth. So it is safe to oversubscribe ISL ports, but you need to be careful when you do it. Make sure you do your measurements and make sure you get your sums right when getting your oversubscription ratios right. Now on a switch where all ports run at the same speed, oversubscription is the simplest math you could hope for. It's merely a ratio of N ports to E ports. In our previous example that we mentioned, with 22 host ports at 8 gig and 2 E ports or ISLs at 8 gig, the ratio would have been 11:1. Storage ports are also commonly oversubscribed, as multiple hosts often access a smaller number of storage ports. So if a single storage port connected to a switch at 8 gigabits per second and 10 hosts connected at 8 gig to the same switch and was zoned with that single storage port, the oversubscription ratio in this instance would be 10:1. Now let's talk about fabric topologies and fabric services.